Hi, my name is Matt Grant, and I'm going to talk about the A-star pathfinding algorithm and applying it to stochastic environments. First, what is a stochastic environment? It's just an environment that has some element of randomness to it. The easiest example is a card game. Assuming the deck is shuffled well, you'll be playing a random set of cards from the deck each game. The stochastic game we'll be playing is, of course, Mario. By itself, Mario isn't much of a stochastic game, so I've made it a little more random by adding noise to it. Whenever Mario tries to move, there's a chance that he either won't move or will do a completely different move. The reason I've done this is, without noise, the A-star algorithm can play the game perfectly on its own. Just in case you aren't familiar with A-star, here's a refresher. A-star is an algorithm used to find the shortest path between two nodes in a graph. It evaluates nodes by the cost to get to the proposed node from the current node, this is notated as g of x, as well as the estimated cost from the proposed node to the goal, notated as h of x and also referred to as a heuristic. As long as there are no negative costs and the heuristic never overestimates the cost to the goal, A-star is guaranteed to find the shortest path between the start and the goal. A-star is very powerful, however it has a couple of problems. Vanilla A-star has two large issues in the context of playing games. First, it doesn't work in real time. It takes a snapshot of the current world and finds a path through it without accounting for how the world will change as time passes. Second, it doesn't have a way to account for stochastism. It only deals with the optimal path. So, how do we solve these problems? To solve the real-time issue, instead of pathfinding through nodes, I've modified the algorithm to run a simulator parallel to the game and ask the game engine what a scenario at a given time would look like. It then evaluates the cost and the heuristic based on the entire state of the game rather than just a position. This lets the algorithm search through both position and time. However, it also introduces issues like keeping the simulator synchronized with the game. Dealing with randomness is much easier when the search nodes are entire game states. This way we can simply bake the probability of noise occurring into the node's cost function and optimize performance by avoiding risky game states. Another solution to the problem is simply to ignore noise and replan after noise occurs. However, this solution is expensive. The solution I've implemented uses a Markov chain to keep track of the probability of noise occurring. I've also implemented a second solution that uses both the Markov chain and a replanning system. Here are a couple of runs. Both of them have noise, however, one has a strategy for dealing with noise and one does not. On the left side, you can see the run that doesn't have a strategy for dealing with noise. It has problems even moving smoothly. However, on the right side, we can see that the run with the strategy for dealing with noise finishes the game easily. For the sake of the viewer, I cut off the run without a strategy. Here are a couple of graphs that show performance changes as noise increases. The average score over 50 trials is notated on the y-axis, and the percent probability of noise is notated on the x-axis. I've used two different kinds of noise, one where the move gets entirely ignored, and another where the move is substituted with another randomly chosen move. These are denoted by cancel and rand respectively. This graph has all the results aggregated onto one set of axes. This makes it a little easier to see that the Markovian strategy starts off a little less performant, but maintains that performance throughout noise changes. The non-Markovian tests were cut off after 50% noise because the results sank too low to gather any meaningful data from the tests. Here are all the individual results. It can be seen that as noise increases, performance generally decreases. The trials that had a replanning strategy were generally able to avoid a large penalty in score till about 20% noise, whereas the runs without any strategy immediately saw large penalties. For the Markovian strategies, the probability of noise doesn't necessarily increase as much as it switches between making noise more or less likely if the previous action had noise. There is a complete explanation of what's going on located in my GitHub repo. Speaking of GitHub, here are some links to the repository. It contains extremely thorough documentation on how everything works and how it was implemented. It goes line by line. It also has supplementary documentation on how to use the Mario AI 2009 framework if you're interested. Finally, there's a link to my code credits document also available on my GitHub repository. These links are also available in the video description. Thank you for watching.